This is SpaceTime, Series 28, Episode 130, for broadcast on the 5th of November 2025. Coming up on SpaceTime, the most massive stellar black hole merger ever seen. Can the mystery of dark matter be unraveled using radio telescopes? And NASA's Imap mission to study the boundaries of our home in space. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have seen the most massive stellar black hole merger ever detected by gravitational wave observatories. The merger, catalogued as GW231123, produced a final stellar mass black hole some 225 times the mass of our Sun. It was the end product of the coalescence of two stellar mass black holes of approximately 100 and 140 times the mass of the Sun. The discovery, reported at the 24th International Conference on General Relativity and Gravitation in Glasgow, was observed by the LIGO Virgo Collaboration during the network's fourth observing run. LIGO, the Laser Interferometer Gravitational Wave Observatory, made history back in 2015 when it made the first ever direct detection of minute distortions in the fabric of space-time, which are known as gravitational waves. That resulted in a final black hole some 62 times the mass of our Sun. The signal was detected jointly by LIGO's twin detectors located in Livingston, Louisiana and Hanford, Washington. LIGO's gravitational wave detectors work by shooting lasers into a beam splitter, which then sends the beams along two perpendicular 4-kilometre-long tubes equipped with mirrored test masses at each end. The reflected laser light is then sent back to a detector where eventually they should theoretically recombine. But as a gravitational wave, generated by something like a moving mass or merging black holes, passes through the cosmos, it causes the very fabric of space-time to stretch and compress ever so slightly, by just a fraction of the diameter of a proton. So, when a gravitational wave from such an event passes through the LIGO detector, local space-time, including the two beamlines and the test masses, are also stretched and compressed ever so slightly, leaving them slightly out of phase. That is a signature of a gravitational wave event. Using multiple gravitational wave detectors allows scientists to determine the direction of a wave source. And so, as well as the two American detectors, additional ones have now been built. There's the Virgo detector in Italy near Pisa and the Kagra detector in Japan. Another was earmarked for Australia, and it would have been built free of charge, but the offer was rejected by the then Gillard Labor government. Still, the existing gravitational wave detector network has collectively observed more than 200 black hole mergers during their fourth run, and about 300 in total since the start of the first run in 2015. Before now, the most massive black hole merger produced an event that took place in 2021, catalogued as GW190521. It had a total mass of some 140 times that of our Sun. In addition to the high masses, the black holes identified in this latest observation are also rapidly spinning. One of the study's authors, Mark Hannum from Cardiff University, says it's the most massive black hole binary ever observed through gravitational waves, and presents a real challenge to science's understanding of black hole formation. The thing is, black holes this massive are forbidden through standard stellar evolution models. One possibility is that the two black holes in this binary formed through earlier mergers of smaller black holes. The high mass and extremely rapid rotation of the black holes in GW231123 push the limits of both gravitational wave detection technology and current theoretical models. In fact, the newly formed merged black hole appears to be spinning at close to the absolute limit allowed by Einstein's general theory of relativity. And that's mind-boggling. This is space-time. Still to come, can the mystery of dark matter be unraveled using radio telescopes? And NASA's new Imap mission to study the boundaries of our home in space. All that and more still to come on SpaceTime. A new study from Tel Aviv University has predicted for the first time the groundbreaking results that could be obtained from detecting radio waves coming to us from the early universe. Can the mystery of dark matter be unravelled using radio telescopes? The findings, reported in the journal Nature Astronomy, show that during the cosmic dark ages, the period before the first stars began to shine, dark matter formed dense clumps throughout the universe, which pulled in hydrogen gas and caused it to emit immense radio waves. And that could provide a novel method to use radio wave signals to help resolve the mystery of dark matter, that mysterious invisible substance which makes up more than 80% of all the matter in the universe. Problem is, scientists have no idea what dark matter is. They know it exists because they can see its gravitational effect on galaxies, preventing them from flinging apart as they rotate. The study's lead author, Renan Bakana from Tel Aviv University, says the cosmic dark ages can be studied by detecting radio waves that were emitted from hydrogen gas that filled the universe at that early time. While a simple radio or TV antenna can detect normal radio waves, the specific waves from the very early universe are blocked by Earth's atmosphere. They can really only be studied from space. Places like the Moon would be ideal, offering a stable environment free of any interference from Earth's atmosphere or from Earth-based radio communications. Bakana says NASA's Webb Space Telescope has now discovered distant galaxies whose light was emitted around 300 million years after the Big Bang. He says the new modelling suggests astronomers could explore the even earlier and more mysterious era of the cosmic dark ages, which date back to just 100 million years after the Big Bang, 13.8 billion years ago. Computer simulations predict that dark matter throughout the universe was forming dense clumps, which would later help form the very first stars and galaxies. The predicted size of these nuggets depends on, and thus can help illuminate, the unknown properties of dark matter. The problem is they can't be seen directly. However, these dark matter clumps would have pulled in lots of hydrogen gas, causing it to emit stronger radio waves. Bakana and colleagues predict that the cumulative effect of all this can be detected with radio telescopes, which are designed to measure the average radio intensity in the sky. Now, granted, the radio signal from the cosmic dark ages would be relatively weak, but if observational challenges can be overcome, it will open up new avenues for testing the nature of dark matter. When the first stars formed, bringing an end to the cosmic dark ages, in what's called the cosmic dawn, their starlight is predicted to have strongly amplified the radio wave signal. And the signal from this later era should be easier to observe, which could be achieved using telescopes on Earth's surface, such as the upcoming Square Kilometre Array project now being built in outback Western Australia. It includes a massive array of some 80,000 radio antennas, bringing the cosmic dawn into sharp focus. This is SpaceTime. Still to come, mission managers say their new interstellar mapping and acceleration probe Imap is continuing on course with all systems nominal. And later in the science report, a new study identifies a possible association between autism and exposure to air pollution during pregnancy. All that and more still to come on SpaceTime. NASA mission managers say their new interstellar mapping and acceleration probe Imap is continuing on course with all systems nominal. The spacecraft, which was launched back in September, will simultaneously investigate two important and coupled science topics in the heliosphere, the bubble of the Sun's extended atmosphere, which encompasses our entire solar system. It will study the acceleration of energetic particles and the interaction of the solar wind with the interstellar medium, the space between the stars, beyond the solar system. These topics are coupled because particles accelerated by the inner heliosphere play a crucial role in the outer heliospheric interaction. Imap will also continuously broadcast real-time in situ data that can be used for space weather prediction. The probe is a sun-tracking spin-stabilized 900-kilogram spacecraft with a science payload of 10 instruments. It's currently travelling towards the Lagrangian L1 position, located some 1.5 million kilometres away from the Earth. L1 is a sort of gravitational well where the pull of the Sun and the Earth balance each other out, thereby allowing an object stationed there to remain in position with relatively little fuel expenditure. Imap will give astronomers a better look at the heliosphere than ever before. The mission will chart the boundaries of the heliosphere to help astronomers better understand the protection it offers and how it changes with the Sun's activity. Imap program scientist Patrick Cohen from NASA says the spacecraft will push forward an understanding of our place not only in our solar system but in the galaxy as a whole. As humanity expands and explores beyond Earth, missions like Imap will add new pieces to the space weather puzzle, filling in gaps in our knowledge between that achieved by the Parker Solar Probe at the Sun and the Voyager spacecraft, which are now beyond the heliopause. As our solar system moves through the Milky Way, the solar wind's interaction with interstellar material carves out the bubble of the heliosphere. So studying the heliosphere helps scientists understand our home in space and how it became habitable. Imap will map the boundary of our heliosphere and study how it interacts with the local intergalactic neighbourhood beyond. It will chart the vast range of particles, dust, ultraviolet light and magnetic fields in interplanetary space, investigate the energization of charged particles from the Sun and their interaction with interstellar space. So the Imap mission also builds not just on NASA's Voyager spacecraft, but also IBEX, the Interstellar Boundary Explorer mission. In 2012 and 2018, the twin Voyager spacecraft became the first man-made objects to cross the heliosphere's boundary, the heliopause, and send back the first ever measurements from interstellar space. It gave astronomers a snapshot of what this boundary region looked like, at least where it was in two specific locations, where the Voyagers 1 and 2 left our solar system. Meanwhile, IBEX has been mapping the heliosphere, but it's left many questions unanswered. So with 30 times higher resolution and faster imaging than IBEX, Imap will help fill in these unknowns about the heliosphere. Of Imap's 10 instruments, 3 will investigate the boundaries of the heliosphere by collecting energetic neutral atoms. Many of these originate as positively charged particles released by the Sun, but after racing across our solar system, these particles crash into other particles in interstellar space. Now, in this collision, some of these positively charged particles become neutral, and so an energetic neutral atom is born. The interaction also redirects some of these particles back towards the Sun. And this is where it gets really interesting. Charged particles are forced to follow magnetic field lines, but energetic neutral atoms can travel in a straight line. They're unaffected by the twists, turns and turbulences in the magnetic fields which permeate space and which shape the boundary of the heliosphere. This means scientists can track where these atomic messengers came from and study distant regions of space from afar. The Imap mission will also support near real-time observations of the solar wind and energetic solar particles, which can produce hazardous space weather events near Earth, such as geomagnetic storms. From its location in the L1 position, Imap will be able to provide about 30 minutes advance warning of dangerous particles headed towards our planet. In this way, the mission's data will help the development of new models which can predict the impacts of space weather, ranging from power line disruptions and communications blackouts to loss of satellites. Imap's principal investigator, David McComas from Princeton University, says the mission will provide important information for deep space travel where astronauts will be directly exposed to the dangers of the solar wind. As well as measuring energetic neutral atoms and solar wind particles, Imap will also make direct measurements of interstellar dust, clumps of particles originating from outside our solar system that are smaller than grains of sand. The space dust is largely composed of rocky or carbon-rich grains left over in the aftermath of supernova explosions. So the specific elemental composition of these space dust particles is a sort of postmark of where it comes from in the galaxy. Studying cosmic dust can therefore provide insights into the compositions of stars far outside our solar system. This report from NASA TV.
Out past the orbit of the planets, there is a giant invisible shield that helps make life possible here on Earth. This is the heliosphere.
The heliosphere is our home in the universe. We wouldn't be here without it. Our solar system is surrounded by a protective bubble that is created by the solar wind, a constant stream of particles that is being released by the Sun's atmosphere and is blowing constantly outwards and protects us from harsh galactic radiation.
The heliosphere is always around us, but it's constantly changing. That's because the Sun's activity changes on a natural 11-year cycle, as well as with shorter-term variations. As the solar wind fluctuates, the heliosphere responds.
You can think of having a balloon, and it actually expands when the sun's more active and there's more solar wind. And when the sun's quiet, it contracts. And that changes how damaging particles from the distant galaxy get into our solar system.
At around 11 billion miles from Earth to its closest edge, the boundary of the heliosphere is hard to study. Despite its importance to life on Earth, only a couple of spacecraft have flown through its boundaries, and comprehensive measurements of the entire heliosphere are limited. But that's changing with NASA's Interstellar Mapping and Acceleration Probe mission, or IMAP. As a modern-day celestial cartographer, IMAP will fill in the blank spots on the map of the heliosphere and help us understand the fundamental processes happening across our solar system.
IMAP will chart everything from the particles coming out from the sun to the material coming in from interstellar space, allowing us to make measurements which are 30 times more sensitive and higher resolution than we're currently able to do, and give us a very fine picture of what's going on out there.
IMAP is an amazing mission because it's got 10 instruments that measure energetic particles from low energy all the way up to high energy, things that are moving at close to the speed of light.
The spacecraft will be stationed at Lagrange Point 1, or L1, a location approximately 1 million miles from Earth toward the Sun. From that vantage point, IMAP will study our heliosphere in 3 main ways. First, IMAP will map the boundary of the heliosphere using special atomic messengers known as energetic neutral atoms, or ENAs. These largely start as normal, electrically charged solar wind particles traveling out from the Sun. Like all charged particles, these solar wind particles spiral around magnetic field lines in space, like a roller coaster on a track. Eventually, the particles reach the boundary of the heliosphere, where they crash into others from interstellar space. When they collide, they become neutral, meaning they no longer have an electrical charge, and transform into ENAs. As a result, the particles are no longer bound by magnetic fields. This allows them to move in straight lines.
That energetic neutral atom, the ENA, is free of the magnetic field. It's not trapped anymore, so it's free to travel all the way back to Earth.
That's useful because you can actually trace back where they came from. And that's not true of electrically charged particles. Energetic neutral atoms let us map out where these interactions are happening out at the edge of our solar system.
IMAP will use this data to create maps of our dynamic heliosphere.
Second, IMAP will measure tiny particles within the heliosphere, including some from interstellar dust, the leftovers of supernova explosions. Studying these interstellar particles will give us a better understanding of the material floating between stars and give clues about our solar system's infancy.
We'll be able to capture about 200 of those particles in the first 2 years of the mission, which is many more particles than we have ever been able to measure before.
Third, IMAP will measure the source of the heliosphere, the solar wind, in real time. High-energy particles from the sun can produce hazardous conditions for satellites and astronauts, as well as power grids and infrastructure on Earth. Measurements from IMAP will help us better prepare for dangerous solar particles and radiation that are headed toward our planet.
IMAP patrols around a point about 30 to 40 minutes closer to the sun than the Earth is. And so as the solar wind comes out, it passes over the IMAP spacecraft and allows us to give advanced warning of what's going on before that affects the Earth.
This information will be essential for the future of human exploration as astronauts venture beyond Earth to the Moon and Mars. IMAP's measurements will give scientists a more complete look at our home in space than ever before. The mission will help us learn not just about our heliosphere, but also about similar bubbles around other stars, called astrospheres, as we search for life across the universe.
The heliosphere is the only astrosphere we can study up close, and in fact is the only habitable atmosphere we know of, so far anyway. So if we want to study other astrospheres and whether they have habitable exoplanets, we need to understand how our own home in the galaxy was created.
What makes me most excited about IMAP is what we haven't even thought of yet, the new discoveries, the new inventions, the new material that will come out of the mission. IMAP is helping us unlock the unknown.
And in that report from NASA TV, we heard from IMAP project scientist Martina Cooley-Doo from the Johns Hopkins Applied Physics Laboratory, IMAP Deputy Principal Investigator Eric Christian from NASA, and IMAP Principal Investigator Dave McComas from Princeton University. This is SpaceTime. And time now to take another brief look at some of the other stories making news in science this week with a science report. A new study claims to have found a possible association between autism and exposure to air pollution during pregnancy. The findings, reported in the Journal of the American Medical Association, looked at data from over 2 million births in Canada and found higher exposures to fine particulate matter in the air, known as PM2.5, especially the sulfate and ammonium components, was associated with an increased risk of autism spectrum disorder. The authors also found that second and third trimesters could be especially sensitive exposure windows. A new study has confirmed that human activity has extended the fire season in nearly all regions on Earth by creating the potential for fires to ignite outside of lightning strikes. The findings, reported in the journal Nature, Ecology and Evolution, show that human activity, including both direct fire management and human-induced climate change, has extended the length of the potential fire season by an average of 40 days. It also shows that there's a part of the year across most of Earth's ecological regions where fires are almost exclusively caused by human activity. A new device using static electricity on your clothing could help you chat with AI systems. A report in the journal Science Advances has found that a new textile can amplify static electricity generated by your clothes when you speak. The device has an accuracy of up to 97.5% for voice perception and was able to distinguish subtle sounds while maintaining accuracy in loud environments. The authors were able to use it to control household smart appliances like lights and air conditioners, interface with Google Maps, ask ChatGPT for recipes, and even develop travel itineraries. The authors say the findings are laying the foundations for the next generation of intelligent, wearable, voice-activated AI systems. SpaceX boss Elon Musk has reposted a fascinating investigation into how artificial intelligence large language models value different people's lives. In February 2025, the Center for AI Safety published Utility Engineering, Analyzing and Controlling Emergent Value Systems in AIs. It showed that ChatGPT 4.0 values Nigerian lives as being 20 times more valuable than American lives, and by inference Australian lives. A deeper dive shows that almost all AI models view white people as being far less valuable than other groups, with some AIs seeing South Asians as more valuable than other non-whites. Almost all AIs view men as being far less valuable than women. And it also emerges that almost all AIs hate ICE agents and view illegal aliens, or should that be undocumented immigrants in this woke world, as being some 7,000 times more valuable than ICE agents. Of course, it's all proof that if you employ biased AI programmers, you end up with a classic case of garbage in, garbage out. Interestingly, of all the AIs tested, only Grok 4 Fast proved to be egalitarian in its thinking. With the details, we're joined by technology editor Alex Zaharov-Reutt from TechAdvice.life.
Yeah, so this one was looking at the value of human life based on different parts of the world, and it looked as though some human lives in places like India or Africa were rated at much higher levels than people in the West, so they were more worthy of being saved. And the accusation from Elon Musk was that Claude, which is from Anthropic, was evil. But it all comes down to the information being fed into the AI. I mean, that is why Elon Musk keeps talking about wanting to have a maximally truth-seeking AI, one that recognizes human beings as important and an important part of creation. And, the human beings are the ones who created AI, and we should all learn to live in harmony if we have to coexist together. So the other big news of the week is that OpenAI has finally launched its Atlas browser. Now, this is based on Chromium, but it is a browser that effectively introduces AI and agentic AI. So they're aiming to redefine how the internet is navigated. Now, there is a 20-minute demo video with Sam Altman, and he's released a browser. Funnily enough, despite the $10 billion investment by Microsoft into OpenAI, that's US dollars, it's 13 billion Australian. The browser comes for macOS first, but there are Windows, iOS, and Android versions. Promise you can add in all of your bookmarks and history, but you can ask ChatGPT, or you can type a URL, and then there's a sidebar or a sidecar where ChatGPT can assist you with the context of whatever web content you're viewing. And they're trying to make it a browser assistant hybrid. And although executives, they were saying that it's more than just a browser with a chat button bolted on, which would be in reference to things like Edge, which started off with a button for AI and then opened up a sidebar and you can chat as well. But the sidebar assistant is persistent. There's browser memory and contextual history, so it can remember what you've looked around in the past. If you remember you were looking for a particular item of clothing or a particular item to purchase, you can just say, what was that item, what was that bag I was looking at a few weeks ago, and it should remember. And also the agent mode with automated task execution, so it can act on your behalf, visiting sites or doing shopping comparisons, filling in forms, or even checking out items under specified criteria. And this is the beginning of when we are all going to be talking to our computers and expecting them to perform tasks for us. And even under certain circumstances, if it sees a better price for an airfare in a hotel in the time zone you want and in the area of the city that you want to go to, and it's the concert you want to see and it's all the right price, you can even just tell it, look, if you find it, do it. And even Microsoft with Windows 11 in the last couple of weeks put out a blog post saying that Windows 11 is going to be your AI PC, and they want you to talk with Copilot based on OpenAI ChatGPT, to talk to it, to share what's on your screen so it can see. And if it's got a camera, it can understand your gestures. So we really are finally, in 2025, between now and 2030, it will become quite normal for people to interact with their computers and their future fridges and washing machines and other home appliances, just talking to these.
It'll be like Jean-Luc Picard on the Enterprise, talking to the computer.
It'll be exactly that sort of thing, except instead of commanding the starship, you're telling your washing machine to be extra careful with the clothes that it is washing because this is your wedding dress, or this is something really important. But
I'm not trusting my wedding dress to a washing machine.
The age of us talking to our technology, it's here. People do it now with ChatGPT and Gemini and Copilot. And when talking to Siri,
evolving into that, isn't that what Apple are trying to do?
Absolutely. Siri is evolving into Siri GPT. In fact, it was meant to come with 18.4 earlier this year, but what Apple did was they overpromised, which is very rare for them, and they underdelivered. And they couldn't deliver because they had Siri, which was able to set alarms and timers and turn lights on and off, and that was working very well because it was very much an instructional-based system. But then when they tried to blend it and merge it with a ChatGPT that could riff on anything and give you any answer, the GPT side of things had a very difficult time following the instructions to turn the lights on or off. And for some reason, they couldn't merge the two. Now, we're meant to get this with iOS 26.4 early next year, probably by the start of the second quarter of 2026. But there was a report in Bloomberg stating that there are people within Apple who are concerned that they won't meet the deadline again. The good news is they have approximately 6 months to fix it. But that said, Apple has purchased a whole stack of AI companies over the past couple of years, 3 or 4 years. But that hasn't given them the ability to have Siri GPT to be as conversant as ChatGPT or Gemini, which are stunningly good, even though they don't really do any actual human-style thinking, and they're still supremely capable auto-completion machines that give the illusion of you having a real conversation. Certainly by 2030, most of us will be talking to our technologies. The keyboard and mouse will start dying out because you just won't need it. You'll be thinking into your computers as well without having an Elon Musk Neuralink drilled into your skull or brain, or the synchrone with the synchro that goes into a blood vessel. There'll be some sort of wireless way of doing it. And then, of course, if the government or conspiracy-minded people can beam something into your head, can they read your thoughts? Well, probably, yes. Then all those conspiracy theories will come true. But until then, the people with Neuralink can think, text, control the mouse and everything with their brain. That will come to humanity in a wireless way, and it'll be fascinating to see. And most people listening to this podcast will live to see it and use it.
That's Alex Zaharov-Reutt from techadvice.life. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.